Hello wonderful person, this is Anton, and today we're going to be discussing this relatively new study that proposes something not a lot of physicists considered before. Can spacetime crystallize? In other words, can the spacetime itself become crystal, thus potentially creating some really bizarre effects and, more importantly, solving a lot of mysteries in cosmology? And though this might sound very speculative and somewhat unusual, this is precisely what this new study by Christian Ecker, Florian Ecker, and Daniel Grumeler tries to tackle. And here, just to start, imagine a somewhat strange situation. You're watching a star collapse that should generally result in a supernova. But even though we expect this to become a black hole or a neutron star, for some reason this one star doesn't. It actually finds itself in a kind of a perfect middle ground. A state that's so precise that it seems to represent this threshold between becoming a black hole and still being a star, or to be more precisely, exploding as a supernova. And so in this recent study, published in a Journal of Physics Review Letters, here the paper theoretically explores what happens at this boundary, with results suggesting that the fabric of the universe itself, space-time, actually begins to behave as a kind of a crystal. And that by itself produces additional effects. And so in this video, we're going to take a look at this study and its main propositions, and also how this study actually kind of solves certain problems that stumped physicists for decades. But we'll also discuss what a space-time crystal might be, and why this discovery matters for our understanding of cosmology, the Big Bang, and how maybe one day we might even be able to detect something like this somewhere out there. But because this is such a complex topic, let's define the terms first. And actually let's start with space-time. In our daily lives, we generally separate space and time. We think of them as two separate entities. But since the work of Albert Einstein and Hermann Minkowski, we now know for a fact that space-time is actually a single phenomenon. It's a single four-dimensional continuum. And it's not a static thing, it actually is flexible and can be curved by the presence of mass and energy, which is what we normally refer to as gravity. So basically gravity in this case is the curvature of space-time. Okay, what about crystals? Well, normally when we talk about crystallization, such as what you see here, the crystallization of citric acid, we're essentially talking about atoms and molecules arranging themselves into a highly organized repeating pattern. Basically a structure that's very easy to predict and that repeats itself over and over. But it repeats itself over and over in space. And so in some sense, a space-time crystal is a kind of a similar idea, but instead of atoms repeating in space, it's actually the geometry of space-time itself that starts to create these repeated patterns. And I guess you can sort of imagine it as this. And this happens through something referred to as discrete self-similarity. And so basically, if you were to zoom in, you would see the same pattern of curvature repeating again and again. Kind of like a fractal that echoes both in time and in space in exactly the same way. Although for a three-dimensional human brain, it is extremely difficult to imagine. Although last year, scientists were able to create something like this that kind of mimics this space-time crystal. Here, this created a curvature in space and in time with an extremely similar pattern. And while for a very long time, scientists, and specifically physicists studying black holes, have known that these patterns seem to exist in the mathematics of the black hole formation. But they could only find these patterns using supercomputers. And these equations, known as Einstein field equations, are notoriously difficult to solve because they're nonlinear, where gravity seems to react to its own energy. And well, here the story starts in 1993. And specifically with the Canadian physicist Matthew Chukchuik, who discovered a phenomenon referred to as critical collapse. And so here when matter, and specifically is certain types of massless matter described by certain equations, is turned to the exact threshold between dispersing into space and collapsing, it seems to enter an unusual intermediate state, with computer simulations showing that this threshold exhibits unusual discrete pulses, space-time pulses, that oscillate and repeat following a geometric rhythm. And because the geometry repeats itself at regular intervals, here physicists nicknamed this a space-time crystal. But for over 3 decades, finding the exact formula for this and especially the exact explanation and description of how to make this, proved to be notoriously difficult because of nonlinear complexity of Einsteinian equations. Or basically because when it comes to gravity, trying to calculate things in 4 dimensions is exceptionally difficult. And while one of the main achievements in the study is basically finding a way to solve these equations analytically, essentially by using pen and paper and not supercomputers. And this is where this new technique known as large D expansion comes in. And the trick here is very clever. Instead of trying to solve the gravity in 4 dimensions, basically in real spacetime, researchers looked at what happens if the universe had an extremely large number of dimensions represented by letter D. And surprisingly, in this limit, the equations simplified dramatically, allowing the calculations to progress very fast. And by solving the problem for a theoretical universe with, for example, 300 dimensions, they could then work backwards to find solutions that seems to work for 4-dimensional reality as well. And what they found was an infinite family of very specific solutions that describe how spacetime crystallizes right at the moment a black hole is about to form. In other words, right at this point, spacetime seems to create a perfect crystal. Okay, cool, but how does this explain anything, and what does any of this mean? Well, aside from this being a very interesting mathematical triumph, this has a massive implication for cosmology. And that's because in cosmology and in astrophysics, there are obviously these 2 main problems, or 2 main mysteries. First, how exactly did the universe start right before the Big Bang? And what happens inside black holes? And both of these concepts, as of today, rely on this idea of singularity, or this initial singularity that we think the universe potentially started with, and the black hole singularity that a lot of mass seems to condense into. Or basically this point where density and temperature seem to be infinite, but also don't really make sense in terms of actual reality, because we don't really think infinity should exist. And so technically the current laws of physics, especially general relativity, completely break down at this point. We don't actually have any physics to explain any of this. But this newer proposed spacetime crystal potentially creates a solution for this naked singularity. In other words, we might have our first mathematical idea that can maybe explain what happens inside black holes, and of course, how the universe began. And by understanding these space-time crystals, we might also get closer to the theory of quantum gravity, basically a kind of a holy grail of modern astrophysics, an idea that might finally be able to directly connect quantum physics and general relativity, which are basically both extremely successful independently, but don't seem to have any connection between them. And to some extent, this study also potentially relates and even explains primordial black holes. Basically these hypothetical black holes that could have formed in the incredibly dense environment in the early universe, and black holes that could also maybe explain the phenomenon we refer to as dark matter. And so here, long before any stars existed, and when the universe was extremely compact and extremely hot, and even before it underwent a critical collapse, the whole universe could have been actually filled with these space-time crystals, some of which could have become primordial black holes. But as the universe transitioned from a more crystallized state into the state that it is today, these crystals collapsed into black holes, and everything else became expanding space-time. And in some sense, I guess you can kind of compare it to crystallized ice melting into water, or maybe even eventually becoming vapor. So this is essentially a kind of a transition between different phases. And since some of the recent observations from the James Webb have actually found unexpectedly large galaxies, enormous black holes, and even more black holes than we ever expected, some researchers now believe that primordial black holes might have been actually prevalent everywhere and might even have served as seeds for many different early galaxies to basically grow around, developing into galaxies we have today. In other words, here, assuming this is correct, it all started with the crystallized spacetime, which then transformed into something else with some of the crystals collapsing into black holes, and these black holes slowly acquiring more mass and more gas and becoming galaxies over time. Okay, well, theoretically this is obviously really interesting, but what about actual physical proof? Or basically, is there any way to prove any of this? Because right now this is all just a bunch of clever math. Well, the answer seems to be yes, and it seems to be in gravitational waves. And so basically here, when two black holes collide, And when they produce ripples in fabric of spacetime, there might be certain signs that we can detect over time. And so if this spacetime crystal hypothesis is correct, a lot of these merges should be producing certain types of echoes, representing slight repetitions in the gravitational wave signal that seems to happen at very specific intervals. But the problem is that, because they would have such a small amplitude, they would be actually pretty difficult to find. And while current detectors, such as LIGO and Virgo, even though they found quite a few black hole mergers, might actually not be sensitive enough to find these faint echoes for now. But because with time they always get upgraded and become even more sensitive, the next generation of detectors, and especially the project referred to as the Einstein telescope, will definitely have the necessary precision to discover some of these patterns. And so if these echoes and these patterns are discovered, they would definitely be the smoking gun for the crystallization of spacetime, confirming this hypothesis and essentially explaining what happens inside singularities, or to be more exact, how gravity behaves at these thresholds between black holes and exploding stars, and how some black holes potentially collapsed in order to form the mysterious dark matter. And this is of course a very interesting reminder that in just the last few decades, we've basically moved from seeing black holes as a kind of a chaotic, unpredictable event to seeing it as something that we can now understand, analyze, calculate, and even use to solve various mysteries. And in this case, in this study, by looking at the universe through the lens of many dimensions, researchers found a way to simplify some of the most complex equations in existence. And this research, once again, is not just about black holes, it is about the beginning of everything, that moment right before the Big Bang. And so if spacetime can crystallize, then the chaos of the Big Bang might have actually been a highly organized structure that we are only now just beginning to understand. But as always, we need more studies and more data before any conclusions can be made. Although in this case, the math is definitely intriguing. On that note, once we discover something else, we'll definitely come back and discuss this in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining the channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.